नमस्ते बच्चों, हमेशा खुश रहो बच्चों। माई सेल्फ ओम प्रकाश केसरी, फैकल्टी ऑफ डिपार्टमेंट ऑफ मैथमेटिक्स अंडर फैकल्टी ऑफ एजुकेशन एंड मेथोलॉजी। टुडे आई taught you topology on R, which is the subject of topology which I taught in MSc Mathematics first semester student. These are the lesson planning which are already discussed in your first introduction class. These are the step for planning a lesson which are already discussed in your first lecture class. These are the components of a lesson plan which we have already discussed in your orientation program class. Now, topology is the subject of mathematics under science stream, and this subject is taught in MSc Mathematics first semester student. In your last class, I will see the concept of completeness and compactness. Now, today I will see recapping on this first. The completeness is set K or real number is said to be complete if every Cauchy sequence xn of point in K converges to a point in K. Of point in K converges to a point in K. That means it has a limit point inside the set. And for example, we see the set of integers is a complete. Set of real number is complete, but set of rational number is not complete. Next is the compactness. A subset K of R is said to be compact if every family of open interval of R whose union contain K has a finite subfamily which also covers K. Has a finite subfamily which also covers K. And we also noted that the every compact set is closed and bounded, and hence the Henny-Borel theorem state that every closed and bounded set is in R is compact. Every closed and bounded set in R is compact. For example, every finite set is compact. That means if a set is finite, then it must be compact. The infinite set 0, 1, 1 by 2, 1 by 3 dot is compact. Every closed and bounded interval is compact, but R itself is not compact. But R itself is not compact. R is closed as well as bounded, but it's not compact. Every closed and bounded interval is compact, and Henny-Borel theorem also says that. Now next is the connectedness. A set K of R is said to be connected if a set K of R is said to be connected if the segment joining any 2 point of K, the segment joining any 2 point of K lies inside the K, lies in K. Then we can say that K is connected on R. K is connected on R. That means any segment joining any 2 point of K lies in K. Lies in K. That is the connected set is a interval, finite or infinite. That is the connected set is a interval. It may be finite or infinite. It must be one of the form of close interval AB, open close interval AB, close open interval AB, or open interval minus infinity to B, open close interval infinity to B, open interval AB, A to infinity, like that. Clearly R is connected but Q is not. From the above definition, it is clear that R is connected but Q is not. Neither is I. That means set of integer. The set A, set 0, 1 union 2, 5 is also not connected. Is also not connected because when we take a point 1 and 2, the line joining between these 2 points will not be in the set. Note that the union of two connected sets in R did not be connected, but the intersection of the two connected sets is connected. That means the union of any two connected sets in R did not be connected, but the intersection of the any two connected set is connected. With the which will we see in the above example. Next is the continuous function and homomorphism. In your real analysis class, you already discussed the continuous function. Now, a function f from R to R is said to be continuous at a point P if for every epsilon greater than 0 there exists a delta greater than 0 such that function of mod of function of x minus function of p always less than epsilon all, all x satisfying x minus p less than delta, x minus p less than delta, that is x belongs to delta neighborhood of p implies is f of x belongs to delta neighborhood of f of p, f of x implies is delta neighborhood of f of p. Here we choose delta depending upon both p and epsilon, depending upon both p and epsilon. In a particular problem, it does not depend upon p. In some particular problem, it does not depend upon p. Then the continuity is known as uniform continuity. Then the continuity is known as uniform continuity. At that point, we use the mod function, and the function is defined as a function f such that r r to r. A function f from R to R is said to be continuous if it is continuous at every point of R. Is said to be continuous if it is continuous from every point of R. Every point of R, which can be shown with the help of following graphs. This is the graph of f of x is equal to sine x, and this graph is a continuous graph. This graph is a continuous graph, which can be visualized with the help of given diagram. Now, if we find f inverse CD, which is equals to AB union PQ, f inverse CD, which is AB union PQ, AB union PQ, union dot dot dot. Similarly, if we find f inverse CD in this graph, second one, it is an empty set, which is an empty set because C and D are outside the range of the given. In this case, in third one, if we find f inverse CD, which is nothing but whole R, which is nothing but whole R. From the above definition, it follows that the function f is continuous on any subset D of R. For any subset D of R, it is continuous at every point of D, but if D contains some isolated point, that means a point P is an isolated point of a set D if there exists a delta greater than 0 such that delta neighborhood of P intersection D is equals to 5. Then the continuity at this point it is enough to verify whether the function is defined at this point or not. From definition, it is follows that every uniform continuous function is continuous. Every uniform continuous function is continuous. Now, from the discussion of above things, we conclude some points which are as under. The first point is the continuous image of a compact set is compact. The continuous image of compact set is compact, and therefore we can say that bounded and closed. Closed and bounded. And the next one is the continuous image of connected set is connected. I will see previously the continuous image of compact set is compact, and then the continuous image of connected set is connected, and therefore in an interval. A set A is a dense subset of R. A set A is a dense subset of R, then every uniformly continuous. Every uniformly continuous, not simply continuous. Every uniformly continuous function on A can be extended uniformly as uniformly continuous function on R. Can be extended uniquely as uniformly continuous function on R. Now, I'm going to define the homomorphism of a function. You know very well the bisective function. Bisective function is nothing but the 1 1 onto function. The function which has 1 1 as well as onto. That means both side mapping, which follows both side mapping. A bisective function f from R onto R is called a homomorphism if f is bicontinuous. Now, the word bicontinuous means the function f and the inverse function of that function f inverse both are continuous. Then we can say that the function is said to be bicontinuous. That means continuous from the both sides. Clearly, the function, for example, we can take an example: f of x equals to thrice x minus 2 is homomorphism as f is bijective and both f and f inverse are continuous. But g of x equal to sine x is not homomorphism as g of x is not surjective, and hence is not bijective, through it is continuous, only. In your next class I will see the topology on R square. In all these things I will see topology on R, but in your next class I will see topology on R square. This session is powered by the digital version 2.0 JAYOTI Vidyapeeth Women's University Jaipur, and I hope all of you are satisfied with my digital session. If you have any queries, please mention in the comment box. I will try to resolve it. Thank you for watching my this lecture video. Thank you बच्चों.